Now that we've had a chance to spend a significant amount of time actually working and looking at the graphs of trigonometric functions, I actually want to now talk about inverse trigonometric functions. And I want to start by actually looking at the graphs of inverse trigonometric functions and see how these graphs are formed. And while we won't necessarily be responsible for graphing inverse trig functions in this course, I think it's a great place to start because it gives us a good understanding of the domain and range and why we have to do and make restrictions on trigonometric functions in order for there to be an inverse. So let's go back and think about what we know about inverse functions. We know that a function has an inverse function if it passes the horizontal line test. And I'll just write that, the horizontal line test. And what that effectively tells us is that if a graph passes, or if the graph of a function passes the horizontal line test, it tells us that this function is 1 to 1. And just remember what that means. It means that every input corresponds with one output, and that every output corresponds with just one input. So let's look at a couple of trigonometric functions here below. And I've got three graphed right in front of you. Take a moment, make sure you know you can identify which is which. This first function here we see is the sine function. And the next one would be cosine of x. And the final one here would be the tangent of x. Now, let me just kind of zoom in and just focus our attention just on sine for just a moment. So let's take a look at the sine function here. Let's just look at this. All right. So looking at this function here, clearly it's a function. It passes the vertical line test. That is to say that every input has exactly one output. Now, as a follow-up though, I would ask, is this function 1 to 1? And the answer is no, it is not 1 to 1. If I were to draw a horizontal line through the function at some point, I would see that there are multiple instances in which this line is crossing through the function, this horizontal line is crossing through this function, which indicates that for a given output, right, let's say this were, for example, about 2/5, for a given output, there are multiple inputs that correspond with this. So this function is clearly not 1 to 1. So if this function is not 1 to 1, if you think back to what we did with inverse functions, we said that when a function is not 1 to 1, we need to restrict the domain so that this function is indeed 1 to 1. So take a look at this graph here and pause and ask yourself, where could I restrict this function so that it would be 1 to 1 and such that then I would then be able to graph an inverse function for it? Well, the answer is there's many places, right? We could restrict the domain from negative pi, from pi over 2 to 3 pi over 2. That is to say, we could restrict the domain here and here so that what we have, let me actually just change this. This here would be so that this function's domain is now restricted, and now this function in this restricted domain is indeed 1 to 1. And you could go from 3 pi over 2 to 5 pi over 2 and so on and so forth. There's many places where we could do this. However, typically, we restrict the domain from negative pi over 2 to pi over 2. And there isn't a great reason for this. Let me just highlight this region here. There isn't a great reason for this. It's mostly convention. However, it's the one that makes the most sense because it works within the quadrants from negative pi over 2, if we're going from negative pi over 2 to pi over 2, we're looking at the quadrants 1, angles that go up to quadrant 1, and angles that go into quadrant 4 if we're going negative here. Now, so although we could restrict the domain in a number of places, typically sine is restricted from negative pi over 2. Its domain is restricted from negative pi over 2, to positive pi over 2, so that this function is 1 to 1. And again, it's mostly because now we're working with mostly acute angles from negative pi over 2 to positive pi over 2. So we would restrict the domain from negative pi over 2 to positive pi over 2. And we can include those angles as part of our restricted domain so that this function is 1 to 1. And what this means now is when I write the inverse of this function from negative pi over 2 to pi over 2, that inverse will indeed be a function as well. I can now draw a number of horizontal lines so that this function is indeed 1 to 1. Okay? All right. Now let's look at another graph. Let's look at cosine of x. Pause the video right now and ask yourself, where would be a good place to restrict the domain here so that it would be 1 to 1? And hopefully you said from 0 to 1 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 to pi. And if you said from negative pi to 0, that's fine as well, as long as we are restricting the domain so that the function is strictly increasing or strictly decreasing. For convention's sake, we will say that the restricted domain for cosine will be from 0 to pi. This is typically what we work with, so that we're working with angles 0 to pi here, and we're including those angles as part of our restricted domain. Now we see that cosine is 1 to 1 within this interval of 0 to pi. Finally, let's look at tangent and ask yourself, where can I restrict the domain here so that it's 1 to 1? And you might be tempted to think that this function already is 1 to 1, but keep in mind that there are an infinite number of these tangent cycles outside of negative pi over 2 and pi over 2. So in this case, what's nice about tangent is that we naturally have somewhat of a restriction of our domain from negative pi over 2 to positive pi over 2. That is where we have these vertical asymptotes at negative pi over 2 to pi over 2. Everything from negative pi over 2 to pi over 2, we see that this function is 1 to 1. We can draw any horizontal line and it's only going to intersect at one such point. So tangent of x, we would restrict the domain from negative pi over 2 to pi over 2. Notice, however, that I am putting parentheses here. That is because negative pi over 2 and pi over 2 are places where tangent is undefined. So I would not want to include those as part of my restricted domain. It would be undefined at those values. Okay. So now that we see how we can restrict the domain of these trig functions so that they are 1 to 1, let's look at the graphs of these inverse trig functions. So if you recall, how do we ensure, or how do we graph inverse functions in general? What we're going to want to do is we're going to want to switch the x and the y coordinates, because we're switching the domain and range from our function to our inverse function. And this is going to look like a reflection over y is equal to x. Okay, so let's take a look at the sine function first. All right, so we're going to list out some coordinates for the sine function, and then we're going to flip those x and y values to have the points for our inverse. Now, there are a number of angles that we could have chosen to input for x. I might actually go with negative pi over 2, 0, and positive pi over 2. Again, had you done negative pi over 4 to pi over 4, that would have been fine as well. But this is going to give me a pretty good sense as we go from the endpoints of our domain restriction as to what this function is going to look like. Well, what would the inverse of sine look like? This would be negative 1, negative pi over 2, 0, 0, and 1 and positive pi over 2. Now, one quick notation thing that I should point out before I graph this inverse function, you'll notice here that there are two different ways that I am notating that we're finding the inverse of sine. We've got what looks like sine to the negative 1 power of x, and we also have arc sine. Both of these are valid notations for the inverse sine. Please remember, though, that this is not the reciprocal. We're not talking about cosecant here. This negative 1 notation is just a notation for the inverse sine. I am going to recommend that we go with arc sine here. And the reason for this mainly is that when you get to calculus and we start doing derivatives of sine functions, and you'll see the notation for derivatives, it's often a good idea not to mess around with writing these here, because that can mean something else in calculus. So while in this course I would accept either one work, I would recommend writing arc sine instead of that inverse sine notation. But I did want to make sure that you are aware that that is what it meant. Okay, so going back to talking about the inverse sine, let's graph these points now. For arc sine, we would say that when x is equal to negative 1, our y value is equal to negative pi over 2. So at negative 1, I get negative pi over 2. 0 results in 0, and 1 results in pi over 2. Okay, and this graph is going to be a little bit tough to see, but if you were to take the rest of those angle values, like negative pi over 4, pi over 6, and so on, you would get a graph that looks actually something like this. That's what the inverse sine graph looks like. It looks like a reflection of sine of that interval, within that interval, over y equals x. Okay? All right, well, what about something like cosine of x now? Well, again, I'm going to go from the endpoints of our restricted domain. So 0, pi over 2, and pi. 0 and pi are my endpoints of my restricted domain here. My restricted domain, 0 to pi, right? And what are those outputs for cosine at those angles? We have 1, 0, cosine of pi is -1. Now, if I flip those x and y values, I get 1, 0, 0 pi over 2, and -1 and pi. Now, if I graph those as coordinates, 1 results in 0, 0 results in pi over 2, which is right around here, and -1 results in pi, which actually, if I just label here, should be up here. So what does this graph look like? Well, that's probably a little too extreme. So this is going to look something like that. Okay? All right. Now, finally, let's look at tangent here. So let's go to tangent. Okay, so for tangent, I'm going to go from the endpoints of our restricted domain, which is -pi/2 to pi/2. However, I don't want to use these exact angles because remember, tangent of -pi/2 is undefined. So let's instead use something a little before that. So -pi/4, 0 to +pi/4. So that's going to be -1, 0, and 1. Those are the coordinates for tangent. What would the coordinates for arctangent look like? Well, we're just going to flip these around. And then we're going to get a graph that looks something like this. So -1 gives me -pi/4, 0 gives me 0, and 1 gives me +pi/4. So this graph is going to look something like this. Now, if you're looking at this, you should hopefully notice that this is not complete because tangent, if you recall, goes infinitely. The range of tangent, I should say, is -infinity to +infinity, which means that the domain for arctangent, since we're flipping the domain and range, should go infinitely in these directions. Okay, so what we're going to see is this. And what we previously had with tangent were vertical asymptotes, which now become horizontal asymptotes for its inverse. So at pi/2, we're going to have a vertical asymptote or horizontal asymptote, and -pi/2, we're going to have a horizontal asymptote. And this is a good time to now talk about the domain and range of each of these inverse trig functions. For sine, we know that the domain was all real numbers, which means we have to restrict the domain for sine. So the restricted domain for sine is -pi/2 to +pi/2. This becomes the range of arcsine. The domain of our restricted domain becomes the range of arcsine. So -pi/2 to +pi/2. The domain now would be the output, right? So for sine, we went from -1 to +1. That was the range of sine in our restricted domain. That now becomes our domain of arcsine. So from -1 to +1 inclusive. Go ahead and see if you can figure out the domain and range of arc cosine. Well, for sine, we restricted the domain from 0 to pi. So we're going to say now the range of arcsine is 0 to pi. And similar to sine, the range of cosine was from -1 to 1, which means the domain of cosine, arc cosine, is from -1 to 1. Okay? Arctangent, we're seeing here that the domain is going to be all real numbers by looking at a graph. And the range is from -pi/2 to +pi/2, non-inclusive. And if I were to draw all of these in kind of quadrant form so we can see it, we would see that arctangent goes from -pi/2 to +pi/2, non-inclusive. So I'm going to kind of draw this here to show that we don't include those angles, -pi/2 to +pi/2. Sine, that domain, we're going to choose angles in quadrants 1 and quadrants 2. So we're going to include 0 and pi, 0 and pi. And for sine, for arcsine, I should say, we're going to go again from -pi/2 to +pi/2 in quadrants 1 and 4. Quadrants 1 and 4. But this time we are going to include our angles, -pi/2 and +pi/2. Okay? So this conversation about the graphs of these inverse trig functions are not so much that you can become experts as to what the graphs of these inverse trig functions look like, but the most important part of this conversation is really to make sure that we understand the domain and range of these inverse trigonometric functions. Right? That's really what I want you to take away from this lesson, understanding how we got the domain and range, and understanding what our values and outputs for these inverse trig functions should be. So because that's going to help us evaluate these inverse trig functions. So think about evaluating any inverse trig function. So if I were to say, what is the arcsine of 1/2? What am I asking ourselves here? So for something like number 1 here, what I want you to kind of think about is the arcsine of 1/2. The arcsine of 1/2. Oops, sorry about that. The arcsine of 1/2 is the what? It's the angle. It's the angle whose sine is 1/2 within the range. Within the domain of our inverse trig function. So ask yourself, what angle gives me positive 1/2 when I take the sine of it? So let me write that. The sine of what angle gives me positive 1/2? And you might be thinking to yourself, all right, well, I know that I could say pi over 6. Pi over 6 could work, right? Because pi over 6, the y value would be 1/2. But what I could also have is 5 pi over 6. Okay? So if the question were just the sine of what angle gives you 1/2, there are two possible answers. There's 5 pi over 6 and there's pi over 6. However, when I'm asking you what is the arcsine of 1/2, we would only say that the answer is pi over 6. Okay? And why is that? Because 5 pi over 6 is not in the range of inverse sine or arcsine. It's outside of the range for arcsine. Okay? So again, sine of 5 pi over 6 is indeed equal to 1/2. The arcsine of 1 over 2, however, of 1/2 is only pi over 6. This is the only output that we would say. Okay? So same deal for something like let's say this number 4 here. The cosine of what angle gives me root 3 over 2? Well, you might say something like pi over 6 or 5 pi over 6, right? I should say, sorry, pi over 6 or 11 pi over 6. Sorry about that. Either one of those angles would give me positive root 3 over 2, but arc cosine of root 3 over 2 is only pi over 6, because that is the only angle that's within our range of arc cosine. Okay? All right, take a moment right now and think through these, work through these. Pause the video, and then I can come back and give you the solutions when you're done. Well, hopefully you got pi over 4, negative pi over 2, 2 pi over 3, pi over 6. This is undefined, 5 pi over 6, and this is negative pi over 3. Okay? All right, well, if you have any questions on any of those, feel free to leave a comment below, and hope you enjoyed this video on understanding the domain and range of inverse trig functions.